All right, welcome to the lecture covering 3.6. Welcome, Shayla. Glad you can make it tonight as well. We're going to be talking in this particular lecture about absolute value functions. So back in 2.6, when we were looking at different types of equations, we looked at the absolute value equation. And you end up setting up two different equations, one that is equal to the distance in the positive direction and one that is equal to the distance in the negative direction. So we're not going to do so much of that type of thing tonight as say, okay, now how does this translate itself to the graph, and how can we tie in our knowledge of the absolute value function being one of our toolkit functions, and we can see it move through the plane like we studied in 3.5 and learn how to draw out the characteristics of it. So we'll go ahead and get going. Okay, so understanding absolute value. Recall that in its basic form, f of x equals the absolute value of x. The absolute value function is one of our toolkit functions. The absolute value function is commonly thought of as providing the distance, which we spoke about in 2.6, as the reason why everything comes out positive, because it's a distance and we don't have a such thing as a negative distance. We can have positive and negative direction of that distance, but not the distance itself. So that's why absolute value, quote unquote, makes everything positive. It's because it's talking about a distance. But it's absolute value is this distance the number is from the value 0, or we also call that value on a number line the origin. So because we have to think of this distance in its positive or its negative direction, we can sort of think of the absolute value function as a piecewise function. So we have the absolute value of x being positive x if it's in the positive direction and negative x if it's in the negative direction. So if it's greater than or equal to 0, there are your restrictions right there on your domain. If it's greater than or equal to 0, then it comes out in that positive direction. If it's less than 0, it's on the negative side of the number line, so we consider that to be a negative distance. So, well, let me tell you, that's not a negative distance. It's a positive distance in the negative direction. All right, so let's take a look at a quick example here. So this is taking a situation and seeing how it applies to an absolute value equation or function. Students who score within 20 points of 80 will pass a test. Write this as a distance from 80 using absolute value notation. Okay, so let's just think about this in number terms. So let's take a look at a number line. Here's 80. Let's say here's 90, and here's 100, and here's 70. And here's 60. Now, when we say that something lives a distance from another thing or object, or in this case, position on the number line, when we're finding that distance, what we're actually finding is the difference between their position. So Josh and Shayla, what type of operation am I talking about when I'm talking about a difference? Yeah, it's subtraction. Like if I said to you, I don't know, Mary's house is 20 miles away and Larry's house is 30 miles away. What's the distance between them? You would subtract 20 from 30 to get that difference, or that difference between position or distance between them. So if we are wanting the distance from 80 to be equal to 20, what do we need to do? So we know we want the difference, because it's the distance we're talking about. Actually, let's go back to our number line here. The reason I drew the number line this way is because if I'm at 80, I'm right here. I have the possibility, though, of living at 60, because that's 20 away from 80, or I could live at 100, because that's also 20 away from 80. So I want this distance from 80 to be 20. I want the difference, or the difference in position or the distance to be, so it needs to be exactly equal to 20. Since there are two possibilities, one being in the negative direction, one being in the positive direction, I'm going to need to take the absolute value, because what if it ends up being negative 20? Well, I know that that distance can't be negative. It's actually the direction of negative. That's where the absolute value comes in. So I need for this distance to be 80. I'm sorry, to be 20, and it has to be 20 away from 80. I have to have a variable since I'm writing an equation here. So if I subtract 80 from where I've started from, I should end up with either positive 20 or negative 20, but if I take the absolute value of it, then I'll get that positive distance out. Am I clear here? Am I making sense? I feel like I'm a little bit rambly tonight for some reason, but is it clear why I've set this equation up the way I have? Shayla, you can just give, okay, excellent. I've got 2 green checks. I'm being clearer than I feel like I'm being. So you can imagine, okay, if I plug 60 in here, 60 minus 80 is negative 20. Take the absolute value and get 20. If I plug 100 in here, 100 minus 80 is 20, absolute value of 20 is 20. So the most important thing here is that you realize the positioning of everything and what they mean where they are. When we have the absolute value signs, this is always talking about a distance, which is also known as a difference in position. And it always has to come out, let me color code this, there we go. It always has to come out to be a positive value, because distance cannot be negative. So because we're given this range of, well, it's 20 points either way, because we know we're going to end up having a negative direction and a positive direction. That's what's going to clue you into, hey, I've got to use absolute value here to get to these two different places in different directions. All right, we'll go ahead and move forward. I think y'all are good with this. Okay, so graphing an absolute value function, we're just going to look at the XY table or XF of X table for an absolute value function a little bit closer. So you can see the blue graph here is just good old absolute value of X. That's your toolkit function. It hasn't been shifted, it hasn't been stretched, no nothing. So we have f of X equals the absolute value of X. And so if I create a table for that, and it's important that you pretty much memorize all of your toolkit functions, X and f of X tables. The reason it's imperative or very important is because you're going to be transforming from those particular values or coordinates rather. So it's important to know what you're shifting from and what that thing looks like. So first of all, I have to think, okay, are there any domain restrictions on the absolute value? In other words, is there any real number that I can't take the absolute value of? And that answer is no. So my domain here is negative infinity to positive infinity. I don't have to worry about plugging in a value that's going to be undefined or going to create an imaginary number. All right, so we'll just go with good old -2, -1, 0, 1, and 2. Now, you don't have to go with those values, but they're nice and neat and right around the origin. All right, when I plug each of these in, -2, the absolute value of -2, in other words, how far does -2 lie from 0 on the number line? It lies 2 units. Same question with -1. How far does -1, or you could even say 1 in the negative direction, lie from the origin? 1. Okay, so we have 0 lying 0 away from the origin, 1 lying 1, and 2 lying 2. So you can see how this hard V that does come to a point, unlike the parabola, the absolute value function does meet at a vertex. We have -2, 2, -1, 1, 0, 0, 1, 1, and 2, 2. And then you can see it's already graphed for us, obviously. Here's an important thing when you are trying to figure out if you're given other graphs of the absolute value functions. You can see they all make the V's, but they could have been stretched or compressed or shifted up or down. Notice the vertex of the toolkit function is at the origin. And that's going to be a characteristic of all of your toolkit functions. We'll go through the origin. So that's your first clue as to if something is shifted or not. I mean, obviously, this guy up here has shifted 3 to the right and 4 up. And notice we've gone 3 to the right and 4 up with our equation there. But you have to be a little bit more clever to figure out, okay, has this thing been stretched or compressed at all? And in this case, we're shown the equation so we can point it out quickly that yes, we've had a vertical stretch with that particular function, that red function there. You can tell it looks skinnier than the blue one. It's as if you grabbed onto the arrows at the top of the function and pulled them up in the vertical direction without moving your vertex. So it makes it look taller and skinnier. So I just wanted to point out the toolkit function for absolute values x f of x table, note its domain. We can also talk about its range. We can see that this thing is never going to go below the x-axis, which is a y value of 0. So the range goes from 0 inclusive up through positive infinity. And you can't see my comma because there we go. I'll leave it over a little bit. All right, so any questions just about the basic absolute value function? Give me a green check if you're ready to start looking at problems with this. Okay. So, write an equation for the function graph. My suggestion is when you get to these problems like this, the first thing you're going to want to do is think about your toolkit version of the function. So I'm actually going to go back, and I'm going to grab a screenshot of our x f of x table here. And we're going to put this on the graph so we can compare it. Because we want to be able to see if this thing's been stretched or shrunk, and I'll show you another way of looking at it to tell. I meant compressed. The other book that I teach out of, at least through this semester, uses stretch and shrink instead of compress. Every other book I've taught out of in my 13 years has said compress instead of shrink. So I'm actually glad to be getting back to a book that says compress, but apparently old habits die hard. All right, so I'm going to go ahead and put my parent or toolkit form of the function. So -2, -2, -1, -1, 0, 0, 1, 1, 2, 2. And we're trying to see, okay, how does this darker blue function compare to my toolkit version? And you can see, okay, so we know if we're going to write the equation for this particular function, it's got to look like f of x is equal to some sort of absolute value, and I'm leaving room in case we've got other things going on. So I've left room for, let me label what I've left room for. I've left room for vertical stretch or compress, just depending on what that value is. And you can see it's a stretch because it's skinnier than the regular one we have there. If it had been a compress in the vertical direction, it would have been fatter looking, as if you put a weight on the two arrows at the top and it weighted it down towards the x-axis. So that lives as a factor, something that's multiplied, as a factor outside of the absolute value function. Now we can also have a horizontal stretch or compress, but we're not even going to go there. We can express the same stretch or compress vertically as we can horizontally, because a vertical stretch is a horizontal compress. You really can't tell the difference in them. And it's easier to work with and find vertical stretch and compress. So that's what we're going to focus on with this particular problem. All right, let me point this out. Minus lives in the form. So it's always good, no matter what function you're dealing with, if you're trying to figure out, okay, how have I shifted horizontally? You're going to have a subtraction symbol between your variable and the units that you have shifted. So if you have shifted in the negative direction, that's minus a negative, it's going to show up as a plus when you simplify it. So let's take a look at Okay, let me label this. So this is a horizontal shift. And then added outside the function is where we get vertical shift. Right there. Okay? So let's start with the shifting because that's the easiest thing, and then we'll go and figure out how to find how much this thing was stretched or compressed. So I'm going to color code this. In the horizontal direction, we moved 1, 2, 3 to the right to get down to that vertex. So since that's to the right, it's a positive 3 that goes in that position. But notice it says x minus 3. Minus is in the form. So leave it be like that. Even though you went right, it's x minus 3. A vertical shift, so this thing went down 2 between the vertices. So this is a down 2. So we're going to change that plus a negative 2 to minus 2 once we simplify all this. Now we've got to find the stretch slash compress, which we know it's a vertical stretch. So let me show you something here. With my toolkit function, I can go up 1 and over either way to get 1 unit to get to another point on the graph. So up 1 and over either left or right, and that takes me to my next point on the graph. So this is a 1 in the vertical direction and a 1 in the horizontal direction. Now notice I have to go up 2 and over 1 in either direction to get to the next point on my transformed function. So I am suspecting, because I had to move 1 vertically for my toolkit function and I had to move 2 vertically for my transform function, I'm suspecting that the stretch is 2. But guessing and suspecting is not good algebraic practice. We want to know how to actually calculate what that value is. So right now, that is the only thing that we don't know about this function. So I could say at this point, we're at f of x equals some value. We'll call that value a because it's standard to have a in that position there, standing for your vertical stretch or compress on the function, no matter what function it is. X minus 3, and then it's minus 2, because remember we had plus negative 2, and we'll just write that as minus 2. So if somehow I could fill in these pieces, all I'd be left with is 1 variable to solve for. Well, we can fill in for those pieces. And the way we fill in for those pieces is by grabbing a point that lives on our function. So let's take the point, this will be a nice and neat one because it's got 0 as one of its coordinates. We know the point 4, 0 lives on the function. So if I plug 4 in for x and 0 in for f of x, then I'll be able to solve for a. How do I know I can plug in that 0.40 and get a out? Because this equation right here is what I use to generate the points that show up on the absolute value function. So it's perfectly legal for me to pull a point off the function and say, okay, I know this is true, so I can use this to figure out what I don't know about the function. So that's what I'm going to do. 4 equals some A value, some vertical stretch, multiplied by the absolute value of x, which my x, oops, I put the 4 in the wrong place. 4 is actually my x value. 0 is my y value. Okay, so 0 equals A times 4 minus 3 minus 2. Okay, so first thing I'm going to do, now I'm just solving for A. This is the easy part. Just add 2 to both sides. So 2 is equal to some A value times the absolute value of 4 minus 3, which is 1. 2 equals A times the absolute value of 1 is 1. So 2 equals A. So what we suspected was actually correct, that we have a stretch of 2. And we suspected that by looking at the graph. So now I've got to put everything together as the equation for the function. My function is f of x equals 2 times x minus 3 minus 2. Questions about that? Josh or Shayla? Okay. So Josh says he's good, and Shayla says she has no questions. So I think I interpreted y'all's answers correctly. All right. And Shayla, I see you're typing something. Or you were. And Josh, I see you're typing. Okay, Josh gave me the thumbs up. All right, so we'll look at this next one. Write the equation for the absolute value function. So I already know I need f of x equals some absolute value of x, and I'm leaving room for everything else that might. I know it's going to be a minus here. I know it's going to be a plus here. And I know I may have some value out front. All right. So it is horizontally shifted left 2 units. Now, you have to remember horizontal is on the inside because that is the x variable, and vertically is always on the outside of the function. So that's going to happen outside of the absolute value sign. Horizontally shifted left 2 units. Well, left 2 says minus 2. So x minus negative 2 to shift it left. And then we have another characteristic that hasn't come up tonight. It's vertically, so that's outside, vertically flipped. Well, we learned back in 3.5 that when our A value is negative, that it flips over the x-axis, which is a vertical flip. I don't have any stretching or compressing, so this is just a -1 out front that it's going to multiply with. And you don't write the 1. Remember that negative sign out front that's going to be eventually multiplied with what's on the inside of the absolute value sign says multiply -1 by whatever kind of absolute value you happen to get. And then finally, we have it vertically, so we're outside again, shifted up 3 units. Well, up is the positive direction, so it's just a +3. Now I just need to clean this up because WebAssign will not like that minus -2 there. So my final form is f of x equals negative absolute value of x plus 2 plus 3. Screen check if you're ready to move forward. Okay. So a general note, for real numbers A and B in the equation form, absolute value of A is equal to B, with B being greater than or equal to 0. So this is talking about that distance in the positive direction. It's going to have solutions. I'm sorry. B being greater than or equal to 0 means we're talking about a distance here. Because that B's always got to be positive. You can't take an absolute value and have that equal a negative number because absolute value is talking about a distance. And it's saying it's going to have solutions of B in the positive direction, that distance B in the positive direction, or that distance B in the negative direction. Now it also notes if you have the absolute value of A equaling a negative B, in other words, if B is less than 0, this thing has no solutions to it. Because you can't say, yeah, I drove negative 20 miles to get to my grandmother's house because I drove my car in reverse. Does that mean you went a negative distance? No. It just means you probably unwisely drove your car in reverse that same positive distance. We learned this from Ferris Bueller's Day Off when he tried to run the car in reverse to take the miles off of it. And it just put more, yeah, exactly. It just put more miles on the car because there's no such thing as negative distance. All right, so given the formula for an absolute value function, you can find the horizontal intercepts. Okay, so you missed that part of that movie, Josh? That's like one of the best scenes in the movie. He's trying to take the miles off of his dad's, I can't remember if it was a Corvette. It was like it's an antique, like classic red convertible car that they had put on. They put all these miles on it joyriding that day. They skipped school. And so their plan was to jack it up in his dad's garage and run it in reverse to take the miles off. And what happened is it fell off of the jacks and went sailing through the back of the glassed-in garage and crashed into the forest surrounding it. Yes. So lesson learned. You cannot take mileage off by running your car in reverse. Okay, so let me actually go back to a picture of our absolute value function. And I'm going to clean this graph off here so all you see is the function we were dealing with. Okay, notice on our horizontal axis, which is our x-axis, this particular absolute value function crosses the x-axis in two places. The coordinates of those points are 2, 0 and 4, 0. So those special points where a graph crosses the x-axis are known as x-intercepts. And also, just for the record, it crosses on the y-axis up here at 4, 0. No, 0, 4. That's a y-intercept. But we're focusing on the x-intercepts right now. When we're talking about graphs, these are also called zeros. They're called zeros because that's where the y value is 0. They're also called roots. They're also called solutions, and we'll end up hitting up all these words throughout this semester. But the main thing I want you to notice about these x-intercepts are the fact that they each have 0 as their y value. So no matter where you are on the x-axis, your y value is always 0. That's how you find x-intercepts. You find them by plugging in 0 for y. So let's go back to the problem. The problem says, too forward. Okay. The problem says, find the values of x such that f of x is equal to 0. What they're asking you to find are the x-intercepts. They just didn't use that language. Notice in your book it says finding the zeros. I told you they're also called zeros. So I'm given the equation. And actually, I added the graph on my own. I mean, I guess we could, I'll take that. We'll take a look at it here in a minute. It is very stretched though. It's considered either compressed in the vertical or stretched in the horizontal, so it should be really fat looking. So if we want to find where this thing crosses the x-axis, we take the equation. We've got 2 points that we're trying to figure out. Sorry, I can't get my colors straight here. So we start out with the equation f of x is equal to 4x plus 1 minus 7. And since we're trying to figure out where these things cross the x-axis, we need to plug in 0 for y, or 0 for f of x. So 0 equals absolute value of 4x plus 1 minus 7. And now we want to solve this absolute value equation. So I'd add 7 to both sides. Y'all know how to do this. You did this in 2.6. Add 7 to both sides. And I get that distance 7, okay, equal to 4x plus 1. Okay, let me tell you what this says. This says, for what values, that's my variable, x, for what values can I multiply that value by 4, add 1 to it, and land a distance of 7 from the origin? So I need to consider, well, I could have had that value happen in the positive direction with a distance of 7, or I could have had this happen in the negative direction with a distance of 7. And then you just solve each of those little piddly linear equations by themselves. Subtract 1, and get 4x is equal to 6. Oh my God, we're going to end up with a fraction. Oh, the humanity. Divide by 4. And I end up with x is 6/4, which simplifies to 3/2. In other words, 1 1/2, if you wanted to look at it on the graph. Let's do that. So I knew there was a reason I put a graph on here. So we just found an x-intercept. I've got one x-intercept, or 0, whatever you want to call it, at 1 1/2 on the x-axis. So I know it's hard to see because I screenshotted this, but each square is counting by 1s, and this is 5 right here, and that's 10. So if I'm at 1 1/2 on the x-axis, I'm about right here. Okay? And then I can also be, subtract 1, and in this direction, that leaves me with 4x is equal to -8. Divide both sides by 4. And I get x is -2. So I have 2 x-intercepts. All right. And so I'll put that on the graph as well. Let's see, 1, 2, right here. So I've got my two x-intercepts. Let's see, what's half of, let's see, those x-intercepts are 1, 2, 3.5 away from each other. Half of 3.5 is 1.75. So let's see, 1.75 and 1.6. My vertex is going to be have an x value of negative 0.25. So I'm not going to worry about graphing the rest of this. This is what you need to know, though, that that's where that thing, oops, I missed it. That's where that thing crosses the x-axis. It crosses it in two places. It's going to come down to an x value of negative 2.5 and then go back up. All right. Y'all good so far with that? You understand the x-intercepts? Awesome. Okay, so here's another one to practice with. Same thing. Find the values of x such that f of x is equal to 0. So I start out with my function f of x equal to absolute value of 2x minus 1 minus 3. I need to plug in 0 for f of x because I'm looking for the x-intercepts. And I always get that by plugging 0 in for y. 2x minus 1 minus 3. And I need to isolate the absolute value function so that I can understand what distance this is talking about. Okay, and there we go. Now we're looking for whatever values we can multiply by 2 and subtract 1 from and land a distance of 3 in either direction from the origin. Sorry. Good night. It's been a long week. So I have it in the positive direction. 2x minus 1 equals 3 in the positive. So I add 1 to both sides. 2x is 4. Divide by 2. So I have an x-intercept of 2, which is right here. And I could have 2x minus 1 equal to negative 3. Add 1. 2x is negative 2. X is negative 1. The negative 1. So this is going to look something like this. If you went through the whole building the f of x table, which is, I mean, it's not difficult. I just don't want to spend the time to do it because I think y'all understand what you need to understand to get through this particular section. The last thing we have to look at is right here. Should we always expect 2 answers when solving these equations? The answer to that question is 100% no. You should not always expect 2 answers because this one has 2 solutions, but look, this one only has 1 solution. When the vertex is sitting on the x-axis, you're only going to have 1 solution. And what if you've got it floating? Then you have no solution. So that's how you can know how many solutions you should expect. That's all I got for you. Are y'all good with everything? This is a super simple section. Quick, to the point. You should be able to knock your homework out of the park. Shayla, I see you're typing something, so I'm just going to wait to see what you have to say. Yes, you're right, Shayla. This has been like a breath of fresh air after especially 3.5. When I started recording 3.5 on Monday morning, and I just got through shifting, and I was in an hour, I was like, holy cow. I knew that teaching out of the other book, it usually took me 2 days to get through that section, but I did not even imagine that it would literally be 2 hours and 15 minutes worth of lecture. So I was spent. So this is a nice way to end the week for us. All right. Well, if y'all don't have any questions, thank you so much for coming